Good afternoon, everyone. So I hope I'm audible. Welcome to live session 3. So I'm Dr. A. Ramya, Assistant Professor in the Department of Electronics and Communication Engineering in Sri Venkateshwara College of Engineering, Sri Perumbudur. I'm the teaching assistant for the course Functional and Conceptual Design under the guidance of Professor Asokan T. in the Department of Engineering Design, IIT Madras. So I have prepared these live session materials based on his NPTEL lecture and guidance. So today we'll move on to the content. So we have already seen week 1 to week 5, and today we'll be discussing about a HOQ from week 5 and week 6, which is on functional decomposition and fast method. So we've already discussed what are the course learning outcomes. Let me move on to today's topic, which is quality and quality function deployment, that is QFD. So first thing, why do we need QFD? QFD is used to systematically translate customer needs into technical solutions. That is the main reason for going for QFD, and it has 4 advantages. That is, it find weakly satisfied customer needs, and it can also help us identify dependencies and interrelationships among the needs. That is, it reveals how different requirements and technical characteristics influence each other. And the third one, it helps to determine product changes that can improve weak areas. And at last, it also provides a structured link between the customer requirements and technical decisions. For these 4 reasons, we go for QFD, which helps us create a structured link between what customers want and what we build. So QFD ensures that the right features are designed the right way to meet customer expectations and achieve product success. So in QFD, we are going to discuss about the HOQ, that is the House of Quality Matrix, in detail. So we start with the voice of the customer, then we undergo QFD process. We are going to discuss this using HOQ matrix. Then we get the engineering characteristics and our development targets. So QFD bridges the gap between what customer wants and what engineer does and deliver. So how did QFD originate? It was initially developed by Yoji Akao, a Japanese person, and it was first applied in 1970s by Mitsubishi. And QFD provides a systematic approach for translating the requirements to technical requirements. This is the rough sketch of how HOQ looks like. It has different segments. We'll discuss that in detail today. So HOQ is a graphical representation. It contains customer requirements, the technical requirements. This is first one. This is the second. Then we have the relationship matrix. After that, we have technical priorities and target values. We also have correlation between the technical requirements, which is shown in the roof. We'll discuss them one by one in detail. So as I already told you, there are 7 segments which are shown in detail here. The first one is the customer requirements. That is on the left side. We start here. We list all the customer requirements. Then we go for functional requirements. That is how we respond to the customer needs. That is the technical requirement. That is the second segment. Then we have relationship between what is on left side, that is customer requirement, and the technical requirement, which is the relationship what versus how. This is third. And fourth one is the correlation. That is this segment of HOQ. And then we have target values. This is 5, this region. Then we have benchmarking information, that is region 6. Then we have technical difficulty for achieving each of the metric, that is region 7. So We'll discuss one by one. We'll take an example and see how to form the HOQ matrix. So as I already mentioned, this is the basic structure of HOQ. That is, it starts with the customer requirements or the needs, then it goes to engineering requirements, then we have the relationship matrix, that is third one. Fourth is the correlation matrix, then we have targets and the technical difficulties. So the procedure is as follows. First, you identify the needs of the customer. Then you identify measurable metrics. That is, we first find out what we need to do. Then we decide how we do it. Then we go for establishing the relationship between needs and metrics. After that, we establish target values. Then we evaluate the technical difficulty. This is the QFT procedure that we are going to follow. So this we discussed in last class already, that is need matrix matrix. It is almost the same thing, that is we list what are our needs first, then we form the relationship legend, that is we correlate. See, for example, need 1, what is the relationship with metric 1? Does it have a stronger relation or moderate relation or weak relationship or no relationship? So this is what we fill first here, that is the customer needs represent what the customer wants. We'll take an example and discuss. Let's see, we want to let's say that we want to design an iced tea brewer, that is we want to make iced tea. So first we list all the customer requirements. Let's say the customer wants a stronger tea, then he says he wants easier provision for adding ice, then he wants an easy way to add the tea to it, then it should be easy to clean, easy to store, and he wants to make a large amount of tea, then it must contain steam. These are the customer requirements. So what are we going to do in the HOQ? We'll first list the customer requirements here. This is the first step. We have got 7 requirements. Now we will translate these 7 requirements into metrics. We are translating it into 9 metrics. So how are we going to achieve these 7 requirements? Let's say we are going to have a metric for temperature of the water, then the time water is in contact with the tea, because we wanted a strong tea, so it is related to contact time. Then they wanted to brew a large amount, so the volume of the tank is also a matter. Like that, we convert the customer needs into 9 metrics here. These 9 metrics form the column. So the 7 needs, that is the watts, are listed in the rows. We have 7 rows now, and now next step, that is step 2, we are listing the um, engineering metrics or characteristics. So we have 9 such columns now. So this is our heart of HOQ. After forming this, we will build on the other steps. So this is the complete HOQ. Let us achieve at this complete HOQ in a step-by-step manner. So first step, I have to list all the 7 needs. So customer requirements is the first step. I have listed all the 7. I'm going to form 7 rows based on the need of the customer. That is step number 1. So what would a customer expect from it? What is the need is first answered, and then the rows are formed. Next, we'll go to filling the importance for each need. So let's say that there are 7 needs, but all the 7 needs may not have same importance. Having a stronger tea gets higher importance, so we are giving 5. We are going to rate it from 1 to 5. So this need gets a weightage of 5. Easy to add ice, 4 out of 5 people are rating it. So this is also having good importance. Then easy to add tea is getting an importance of 4. Easy to clean gets 5 out of 5. Then you have easy to store with the least importance, that is 3. Then we have a large amount of tea is needed, that is getting an importance of 4. Then we have the last one, that is contains steam, that is also getting higher importance. Like that, you uh, give relative importance among all the 7 needs. That is your second step. After doing this, you go to step 3. Let's assume that the customer is saying, I want a stronger tea, but that is not an engineering metric, or you cannot measure it. So for that, we are going to go for metrics. So stronger tea means 2 possible metrics, that is having the water temperature measured or the contact time with the tea and water. So that is how we are going to design the metrics now. We then build the house, that is we build the technical metrics now. So these are the sorry So these are the 9 metrics now. That is water temperature, tea contact time, water volume in tank, existing tea temperature, brewing time, cleaning time, storage height, and steam containment. So these are not mere statements anymore. They are all engineering characteristics now. So the metric has a value expressed in this unit. For example, if you say water temperature, it's going to be mentioned in degrees Celsius. If you say tea contact time, it is going to be mentioned in minutes. So these are all measurable metrics now. So we have filled the customer needs, we have filled the relative importance, then we have already listed all the 9 technical metrics. So the rows are ready and the columns are ready now. What will be the next step? The next step will be to form the relationship legend. So next is the relationship matrix. We are going to classify into 4 categories. That is, strong relationship is the first category, moderate relationship, weak relationship, or no relationship. These are the 4 categories. So we have to ask a question. Does water temperature strongly affect the tea strength? Yes. So does the storage height strongly affect the tea strength? Probably not. Probably not. So the first one gets a strong relationship, that is a circle which is completely colored in black. Then the next one may have weak relationship or a no relationship. So like that, we have to fill the relationship matrix now. So which metric should engineer pay more attention is given by this relationship matrix. So this is step 4. So by now we have filled 1, 2, 3, and this is the fourth one. So all these 4 are over. I'll repeat once again. Customer requirements, the what's are filled first, then we give relative importance for each of the need. Out of the 7 needs, 1, 2, and 3 needs get 5 importance, then 3 gets importance as 4, then the least one is getting an importance of 3. Like this we have to fill. Then we form the um, columns, that is we convert this what into how. So how are we going to measure the metrics? So that is step 3. After that we fill the relationship legend, that is we classify into 4 categories: strong, medium, weak, and blank category. So like this we have to fill the functional requirements and form the relationship legend. Once the relationship matrix is over, we'll go to the step 5, that is we are going to form the correlation matrix, the roof of the HOQ. That is, if we increase one engineering parameter, can it affect another engineering parameter? For example, if we increase the temperature of water, it will obviously affect steam generation. So what is the relationship between the metrics? What is the relationship among the metrics is listed now in the roof of the matrix, that is correlation matrix. The roof does not primarily represent the customer needs, it represents the relationship amongst the house. That is, relationship matrix is the relationship between what and how, that is need and metrics. Correlation matrix is the relationship between metrics itself. So it correlates how and how, which metric is affecting the other metric. For example, here water temperature is affecting steam generation. So metric 1 is affecting metric 2, metric 3 affects metric 4. That is mentioned in roof of the matrix, that is called correlation roof. So now we have completed what is the need. Need is listed first, then we have listed the importance. After the importance we went to the columns, that is the metrics. After mentioning the metrics, we form the relationship, that is strong, moderate, weak, or no relation. After that is done, we went for correlation matrix, that is step 5. So these are the 5 steps that we have completed. Now we'll go to step 6, that is competitive benchmarking. Now we are going to introduce a product to the market. It is not necessary that our product may be the only one in the market. There may be competitors already present in the market. So we need to compare our product based on every need or every metric with its competitors. Suppose there are already three iced tea brewers in the market. How do we know whether our product is actually better or not? So, what we have to do? We have to rank our product with the competitors. Here in the table, I have taken our product as one column, competitor A is another column, and competitor B as a third column. So, we have to compare it based on the customer ratings. So now QFT is telling not only what customer wants, but also whether our product is weak compared to our competitors or not, is also known by observing the QFT. So this is step number 6, that is competitive benchmarking. What we are going to do is our product will be compared with the existing competitors in the market, and we will do the rating based on the customer ratings. So once we do that, we will know where we need to improve and where we are already good at. So our strength and weakness can be understood by going for competitive benchmarking. So this is segment 6, that is competitive ratings. We have our product, we are comparing it with competitor A and competitor B. So each metric has been compared. The water temperature, our product has a rating of 3, whereas competitor A is better, it has rating 4. Likewise, we can compare for each and every metric. This is competitor ratings. The advantage of competitor rating is it tells you what is our strength, it tells us what is our weakness. Knowing the weakness is very important because only then we can improve our product. So for each and every metric, we can compare our product with the competitors and know. So QFT brings customer information and engineering information together in one integrated framework. That is the advantage. Then we go for the seventh step, that is engineering targets. So now we have compared, we need to have certain target, only then we can work towards the target and achieve it. So we know what the customer wants, we know our competitors. So what should our product target be? Only if we fix the target, we can work towards it and get the best rating from the customer. So for example, the need of the customer is strong tea, that is converted to engineering metric as water temperature and contact time. If it has been converted and the competitive benchmarking is done, we have to set the target. So what is the target now? Water temperature should be 90 to 95 degrees Celsius and the contact time should be 3 to 5 minutes. So if we achieve these two targets, then it is possible for us to get good rating and we can design a better product. A metric by itself is not sufficient. So metric is measurable, but metric is not sufficient. We eventually need a target value. Once we have the target value, then we can work towards it and achieve our target. This connects directly with your previous topic, that is target specifications. The last class we discussed how a metric is designed, that is it is the parameter that is being measured along with the value. So from that value, based on that value, we set the target here. So this is step 7, that is till here we have completed. So first step was customer requirements, second step was the relative importance, third we listed the house, that is the functional requirements, how is listed, what importance, then how. After that we formed the relationship legend, that is strong, medium, weak and no relation. So this is listed. So this area is completed now, that is the heart of HOQ is over. After that we went for correlation matrix, that is correlation between each and every metric, that was step number 5. After that we compared with the competitor, that is step number 6. After doing the comparison, we set the target values, that is step number 7. Once the target values So I hope till step number 7 it is clear. Let us now go to step number 8 and 9. So till engineering targets we have completed. Moving on to the next step, that is technical importance and technical difficulty. So technical importance tells us which is more important. That is, there are so many metrics, but we need not know which one is more important among all. Some house are more important than others because they have stronger relationship with important customer needs. See, certain customer needs are given a rating 5, certain are given 4, whereas certain needs are given 3. So there are few metrics which will cover the needs with more importance. So that should be given more weightage. So we are going to classify the metrics based on technical importance now. For example, water temp is very very important when compared to storage height. So water relationship has stronger relationship with the needs, strong T and desired T temperature. So these two are very important. So they get a higher technical importance. So this is point number 8. That is, we are saying technical importance based on um, customer requirements indirectly, or the customer requirements with more weightage. Then the last step is technical difficulty. Suppose we know exactly what we want to achieve. It is always easy to achieve. So here what is difficult and what is easier is achieved. For example, steam containment is very difficult, but cleaning time is easy to achieve. So we are going to rate each and every metric which is easier to achieve and which is very difficult to achieve. For example, if you see metric 1 and 2 are easy to achieve, that is, it is having a rating of 3, whereas the um, third requirement has higher difficulty level. So like this we classify. If we do the classification, our HOQ is finally complete now. We have completed what are customer requirements, its relative importance. Then the third segment, the functional requirements. Fourth step is what we did the matrix, that is strong, medium, weak, and no relationship matrix. After that we went for correlation matrix, that is how are the metrics correlated among themselves. Then we went for competitor rating, that is sixth step. Then seventh step we have engineering targets. Based on the metrics we set what is the target and we will work towards the target. After that we have technical importance and technical difficulty. With this our complete HOQ is done. So when you want to understand this picture, you can just go through this diagram. It will give you a rough idea. It starts with the customer needs and it closes with the technical difficulty. So I have given one more example here. You can go through these HOQs. It will be helpful for your assignment as well as end semester. So I want to summarize here. We started with the customer needs. From the customer needs, in the last week we went to metrics. Then we formed the needs metrics matrix. After that we have competitive benchmarking. Once the benchmarking is done, we have the ideal and marginally acceptable values. With that we went for target specification and we saw what is QFD through HOQ, that is House of Quality Matrix. So now we know what are our engineering priorities and product improvements that needs to be done. So the key takeaways for week 5 is that The customer needs must be translated to measurable criteria. The metrics provide objective measures of the product performance, and the benchmarking supports realistic target setting. QFD identifies relationships and weak points as well. So HOQ connects with the voice of the customer with engineering decisions. So these are the points that is from week 5. Now we'll start mm, week 6, that is useful for your assignment submission on Wednesday. So we are going to discuss in detail about the product function and functional decomposition. We are starting with the product function, then we'll go to functional decomposition using function trees or the flow method in detail. So what are we going to discuss today in detail? It is function. First, let us start with the function. So we are going to start with the customer need, then we have the function to be done by the product, then we go for concept generation. So a clear reproducible relationship between the available input and the desired output of the product is defined as function of a product. So you have input, then based on the input the function is done and it gives a output. For example, you have human force. Based on the human force, the screwdriver is going to deliver rotational output. A function describes what the product does, not necessarily how it is physically implemented. So function is not same as physical solution. So we need to come out of this component oriented thinking and go for function oriented thinking. That is, instead of saying I need a motor, we need to think like this: I need to generate rotational motion. That rotational motion can be achieved using a motor. So motor is a component, not the function itself. So the function is to generate or convert the rotational motion. The component which does that function is a motor here. Like that, we have few more examples. If you take the function cutting or chopping, it can be done by the component blade. Then we would like to import human force, that can be done with the help of handle. Um, or another example is you want to transmit rotation, for that you can make use of shaft. So the important message that I wanted to convey here is that component is not same as function. The same function may be achieved using different solutions or different components. So the functionality is our aim here, not the component. So the customer need can become a function or a constraint. So we need to understand the difference between function and constraints. So a customer requirement can be like straightening the cloth or to generate steam or exert pressure. So these are functions. Mm, if you consider an iron box, it will do the component or the device will do the straightening, it will generate steam, it will exert pressure. These are functions that the customer require. The same customer may require other things like low cost, compact size, or lightweight or reliability. These are not functions, these are constraints which are coming under customer requirements. So we need to understand the difference between function and constraint. So I've listed the functions, the customer requirements of an iron box here. The customer requirement like straightening, generating steam, and exerting pressure becomes the function, whereas low cost, compact size, lightweight, and reliability becomes a constraint. Every customer requirement is either something the product must do, that is, it's a function, or it is something it must satisfy, that is a constraint. A customer requirement can be a function or a constraint. So we are going to do functional decomposition now. That is, we start with the overall product function, then we break it into smaller subfunctions until the functions become easier to understand and solve. That is functional decomposition. We are going to start with a bigger task, then it is broken into small subfunctions. After that, it becomes easier to understand and solve. So why do we do this process? It's a complex product function is difficult to solve for us, so we break it into smaller functions so that it is easier for us. Functional decomposition turns a complex problem into simpler manageable parts that are easier to solve for us. So here I've taken the same electric iron box example. What is the overall function? Straighten out the clothing. So this can be decomposed into four different subfunctions, that is maintain the base plate temperature, generate steam, exert pressure, then you form the base plate. So these are the subfunctions. So each subfunction can be divided further. So first, if you take it as iron box, it is complex. Designing a complete iron box is difficult for us. But if we divide it into subfunctions, it is easy for us to achieve it. Let us take the subfunction, that is the base plate. Maintain the base plate temperature. How can you do it? You can do it by using these lower level subfunctions, that is generate heat, make the temperature uniform, then switch or control the temperature, and store it or transfer the heat. So using these low level functions you can achieve the overall function. The electric iron function tree is composed of different subfunctions, that is it maintains the base plate temperature, it generates steam, it exerts pressure, and it forms the base plate. So these are the subfunctions. By achieving the subfunctions individually, you can attain the overall function. So why do we need functional decomposition? As I already told you, it has many advantages. It helps us understand the product systematically. It helps us break a complex problem into manageable smaller problems. You can identify the smaller functions, generate concepts for individual functions, and you can achieve the overall function. Mm, you can avoid getting attached to a particular component solution. Instead, you can have multiple solutions if you follow this functional decomposition methodology. And a complex function is decomposed into smaller functions. It leads to easier concept generation. So generate and evaluate concepts for each subfunction. So this is the way we can easily solve a bigger problem. So next is the function tree or the fast method, that is you take the function tree and do hierarchical decomposition. Here the generate stream function, it is further divided into four such sub functions. That is, how can you generate steam? You need water for it. So you store the water, then you say generate steam. After that, facilitate addition of water. So adding water at the beginning alone is not sufficient. If you want more water due to over usage, you can add it. Then you can guide the steam to flow in a particular path. So these are sub functions of this function. So I think you can understand the hierarchy now. The overall function is to straighten the clothing. After that, you have major sub functions, which are four listed here. After that, they are further divided into lower level functions. Achieving the lower level function is easier when compared to achieving the overall function at one shot. So this ironing example, I think it will be easy for you to understand function decomposition or functional tree now. So next is, how do I understand the function? So how do I know what functions to identify? So how we are going to do is, we are going to use it do it using a formula, that is well defined function plus noun, that is verb plus noun. If you take a motor, it is going to provide rotation, or if you take a gearbox, it is going to reduce the speed. That is, you have one verb plus noun combination. If you do that, you can easily understand how these functions are built. So if you take any device or any design for that matter, you can explain it using common functional vocabularies. They are listed here. For example, you can explain them using import, transfer, branch, convert, control, or signal. So a common functional vocabulary provides some uniformity. So it provides robust vocabulary for designers who are working in different areas, and it provides a common representation for comparing the products. It's a structured level of detail for decomposition. Using a common functional vocabulary helps us describe, analyze, compare, and design products more effectively. So that is the advantage of going for common basis functions. So these common functions are divided into 8 classes. They are channel, support, connect, branch, provision, control, convert, and signal. We'll see them with example. For example, if you take channel, it is for transferring information or material from one point to another. If you take an example of pipe, it is transferring water from one point to another point. Or if you take a data cable, it is transferring information from one point to another point. Next function is support, that is, it provides um, a foundation or support for the design. Then we have connect. For example, you have joins, it is for connecting two separate entities in a product. Then we have branch, it is for distributing or separating into two. Then we have provision. Provision is like you store or supply something. For example, we have battery or a tank or a reservoir as an example. Then we have control. Control knob, it regulates or changes the value. Then we have convert, that is from one form to you to another form we are going to convert. Then at last we have signal. A signal indicates some value, or it senses and tells us what is the current state now. So can you tell me to which one the switch belongs to? So switch can be used for connecting two points, or it can also be used for branching into two different segments. So how will you name a function now? As I told you, we are going to have verb plus noun. For example, instead of saying the component name motor, we are going to say generate torque. That is, when you want to describe a function, you describe using this verb plus noun format. Generate torque or generate light. The functionality is described using these two words. This method is called FAST, that is function analysis system technique method, where the function is explained using this formula, that is verb plus noun. You transmit force, you supply electricity. Instead of going for the component name, if you describe the function like this, you get multiple solutions. Display the status. So this is an example of function naming rule. So the rule is very simple. You have to have a combination of verb and noun. Shape, material, then store water or regulate electricity are examples of function terms now. So now I think you can understand the function tree, how I have described the function. It is verb plus noun. You say generate steam. So generate is the verb and steam is what you're going to generate. Then exert pressure, form base plate. So maintain base plate temperature. So base plate temperature is the target and we are going to maintain it. So that is how we did the function tree using fast method. Then we'll go for the second approach, that is subtract and operate procedure. So let us take the same example, that is electric iron box. It is a bottom up approach that we are going to see. We are going to identify the smallest isolatable feature or component in that iron box. Let's say, for example, temperature control knob. We'll take that knob, we'll subtract it or remove it. That is, you remove that control knob. You assume that that control knob is absent as of now. So now you ask a question, what are the functions that are lost? So if the control knob is not present, what is lost? A temperature adjustment is lost, temperature regulation is off, then safety is also cut off. So now you have identified what are the functions. You subtract the component or the feature, then you find out what are the functions that are lost because of it. So now you can easily understand the functions. So functional decomposition is done using SOP, that is subtract and operate procedure. This is a bottom up approach where you choose one component and you remove that component or you assume that it is absent and then find out the functions that are missing now. So you can create a function tree based on this analysis. The first approach that we discussed is fast. Using that, you name the functions in the form of verb plus noun. That is first technique. The second technique that we discussed is subtract and operate procedure. That is, you remove a component and then find out what are the functionalities that are lost. So this is the second technique. Now let us take an example of a can opener. So we are going to consider various components in the can opener. Components like handle 1, handle 2, support, blade, crank, wheel, shaft or rivet. We will remove one component and then we will see what are the functional functions that are lost. Let's say we remove the blade. So if blade is removed, you have to ask a question. What functions can no longer be performed or what is lost? So you get an answer. The function that is lost is removing of lid. So therefore, what is the function of a blade now? It provides the function remove lid. I think now it is possible for you to understand the function tree. So by removing a component and observing the last function, we identify the function that component provides. In the absence only, we'll know the value of it, right? So SOP works based on that. So can opener, there are different components. For those components, you have found out what is the function. So handle 1, it import human force. Handle 2, that also imports human force. Then you have support component that it stabilizes the can. Then you have blade that removes the lid. Then you have crank, which is for converting or magnifying the human force. Then we have wheel that stabilize or transmit rotation. Then we have shaft, which is again for transmit rotation. Then we have rivet, which allow rotation. So for each component we have found out what is the function. So we are not into the design now, we are actually understanding the functions that the product perform. So once the function decomposition is done, we can go for the design approach. So we have discussed two methods, that is two approaches, function trees approach and SOP approach. Then these two are simple methods. Then we go for the robust method, that is the function structure or flow method. So instead of going for component wise, we are going to see what is the flow. So function tree asks what we have seen two approaches, that is the function tree or fast method and SOP method. Both ask what are the functions that exist in the product. Now we are going to transit to the next technique, that is function structure technique. We are going to ask how these functions are connected through the flows. So from what we are going to go to how. So the function structure approach is flow method. The product is represented as a functional system. We examine three things, that is what is energy flow, material flow and information flow. So energy flow, if you consider, it is transfer or transformation of energy. If you consider material, it is the transfer of materials. Then if you consider information, it is transfer or processing of the information. These are the three flows that we are going to consider from input to output through the functional system. So on the left side, I have the input flows, which is categorized as energy, material and information. And again on the output side, I categorize it as energy, material and information. The product is treated as a system that receives inputs and produces outputs. That is how you're going to see the system now. That is, if you want to view the electric iron box, you don't view it part by part or component by component. You're going to see it as a functional system. For that functional system, you have certain inputs and you have certain outputs for that system. So this is a black box model, the product as a functional system. You think of it as a black box. For that black box, there are certain inputs. Those inputs are classified as energy, material and information. And from this functional system or the black box, you have certain outputs. Again, the outputs are classified as energy, material and information. This is the functional system model. So I have certain examples for energy, material and information here. If you consider energy, you can have electrical energy, you can have kinetic energy, magnetic energy or heat energy or optical energy as input or output. They can be either in the input flow or output flow. Then if you consider the material, it can be gas, liquid or solid or dust or raw materials, work pieces and components. This is for material flow. And the third category is information flow. It provides decision making capability, that is, the information is flowing here as a signal or as status information or control information. So to summarize, it can be written like this: you have a system, then you have three input flows, that is energy, material and information. On the output also you have these three categories as output, that is energy, material and information. So it is flow of energy, material and information into the system. It goes through the system and comes out of the system as output to achieve its functions. So what is a signal? So this signal may indicate the preparedness or what is received, or when two things are compared or combined, uh, when you divide it or separate it, or when you want to transmit it, tells you the status. So signals may be any one among this, or it may display something on the screen, or it can be a recorded signal. So all these are examples of signal which gives information flow. A signal is a physical form in which information is conveyed. So let us take the example of an electric screwdriver. Here, the overall product function is to loosen or tighten the screw. So using this device, we are going to see what is the functional structure. So what can be the inputs for this device? It may include electricity, human force, human torque, screw or bolt and hand signal as the inputs. What may be the outputs? The outputs may include rotational motion, heat, noise of the device while using it, vibration. Then finally you have tightened or loosened screw as the output. So the electric screwdriver receives various inputs, performs its function and it produces the output. So if you take the electric screwdriver and consider the energy flow, we start with the electricity that is given as the input. Then how is the flow? You store the electricity, you supply the electricity for the device, then you regulate the electricity in the required format. You cannot give an AC signal and ask it to operate. Sometimes you need to regulate it, convert the electrical signal to required form. Then you generate the torque, transmit it, rotate the solid and turn the screw. So this is flow of energy. So where does the electrical energy enter and where does it finally produce the useful work? So it is going to start here, and then the useful work produced is turning of the screw. So now let us go to the next flow, that is material flow. So what are the material? It may import solid, it may secure the solid, then separate the solid and it will guide the solid. That is, it keeps the screw or bit aligned with the hole. Then you rotate the screw to tighten or loosen it. And finally you have contact screw, that is apply contact at the screw head to transmit the rotation. So these are the material flow that is happening here. You start with the screw, that is import solid, then you do these many things to achieve our output. The function structure allow us to track the physical objects moving through the system. So this is an example of material flow. First flow is energy, the second one is material flow. What is remaining? Information flow or the signal flow is pending. Now look at the signal flow. For example, it starts with the hand signal. You need to switch on the um, device. So you're giving a signal. The switch is pressed and you're giving a hand signal. Then you actuate or regulate it. You fix the speed, let's say. That is actuation or regulation. Then you go for control operation. Then you can stop it once it is achieved, once the goal is achieved. So the product has energy plus material plus information flowing through this functional structure. So you can view it as three flows, that is the energy flow, material flow and information flow. So it can combine this and have functional decomposition as shown here. Let me zoom it. So whatever we discussed, the energy flow starts with electricity, supply of electricity, storing and supplying of electricity, regulation and conversion of electrical energy, generating torque, transmitting the torque, rotate the solid and turn the screw. Turning the screw will be done only if the material flow has already happened. That is, you took the screw, you imported it, and then you brought it to the correct required form. Then electrical energy did the function. And the information flow is also important because only when the user turns it on and controls it, you are able to achieve. So all the three flows are related: energy, material, and information flow, which we saw separately as three different flows in the three slides, are now interrelated, and you can see or understand the overall functional decomposition now. This is the same example that sir has already explained in the lecture. I have taken the same example and discussed. I have listed one more example here, which is inkjet printer. What is the overall function? Make hard copies of a soft document. Let's say you're going to print the assignment. You are going to print it from, say, your computer or your mobile phone. There are three flows involved. One is energy. You need to supply electricity for the printer. Then you need to give material. That is, you need to provide paper and ink as a material for the printer. Then you need information. That is, data. What needs to be printed should be given. Then the human energy or the commands. We need to say print it. Only after this information is given, the printer is going to work. So these are the inputs or the resources. What are the outputs or the results? The printout is your output. Along with the printout, you may have heat energy or noise or the reaction force on the paper. So these are the outputs. This is the overall function, input and output. You can see the functional decomposition now. On the energy flow, you have electricity being supplied. It is distributed. Then convert electricity, drive print mechanism, generate heat, dissipate heat, generate noise, and generate reaction force. Actually, noise is not the main product, but it is also an output. So you have material flow here, that is, it imports ink, stores the ink, imports paper, and it stores the paper always. Then you choose a particular single paper, then you print it, and then you spray the ink, then you capture it on the paper and deliver the printout. So all this happens only based on the information received from the user. So you receive the data, that is soft document, you process the data, you generate the print data, then while doing it, there is a control signal given. For example, if it's a color printout, you're going to control the RGB values, then you're going to monitor what is the status. It says currently it's printing, then finally the print is complete means it will display that as well. And it also indicates what is the level of ink available in the toner. So these are the information flows. You have three categories: the energy flow on the first line, then you have material flow and the information flow. So like this, I have one more example: electric pencil sharpener. So there are three such flows listed here. The first one is the energy flow, that is, electricity is being given. You import the electricity, actuate electricity, that is, switch on or off based on your situation. Then you convert the electrical energy into rotation for sharpening the pencil. Then you change the rotational energy using the gear system based on the speed that you need. You transmit, reduce speed and increase torque based on the requirement. So rotational energy to sharpening mechanism, that is the change which is happening here. The second flow is the material flow, that is, you have a pencil being given as a material that should be sharpened here. You have import solid, that is, you import the pencil, you guide the pencil, then you have the process of removal of the wood material to sharpen the lead. Then you have sharpened pencil as well as the shavings, which is one is required, the other one should be disposed properly. So both are outputs here. The user wants a sharpened pencil and the shaving should be disposed properly in a dustbin, so it can be collected here. So that is material flow. If you look at the information flow, the user gives an hand signal like start, then the system receives the signal, it transmits or converts the signal, it does a comparison, like whether it is sharpened or not. It has a sensing mechanism to check whether it is sharpened properly. Then you control or command it. You send command to the motors to start or stop it or control the speed. Then you indicate the feedback. Let's say it's ready means you give a green LED, or if it is not ready or the process is happening means you indicate yellow or red color line. So this is the flow which is listed here. I think with this discussion, it will be easy for you to take your own example and do the assignment. One more example is listed here, that is, you want to make some masala mix, let's say. So you have a mixer grinder here. You understand the overall function of this mixie first. That is, um, what you need to do. You take the grains, you accept it, you seal the mixie, and then you transmit the torque. After that, you produce the grounded grains or the masala, but at the same time you generate noise, and you also produce some vibration. So these are all parallel outputs. So for this you need to do the flow diagram, that is energy flow, material flow, and information flow. If you consider energy flow, it starts with providing electricity from the supply. Then you convert that electrical energy to torque. After that you rotate the blades, that is electrical energy is converted to mechanical energy, the form of rotation. Then you have material flow, that is you accept the grains, you contain the grains, then seal the grain, that is the jar is sealed. After that you chop it, then you make the masala mix. So this is the material flow. Information flow, the switch, the user operates the switch, that is he turns on, then he also tells what is the speed, say 1 2 3, or um off, or reverse mode. Then only he controls the then only he gets the output. So this is the information flow. These examples are already discussed in sir's lecture. You can go through them and you can take up the assignment. And now I would like to conclude what we discussed today. We started with the customer needs, understanding the customer's needs last week. Then we went for HOQ. Last week I could not discuss HOQ, so today we discussed HOQ. Then we went for functional decomposition today, where we saw three techniques. One is the fast method, the other one is SOP method. These two are helping us draw the function tree. These are simple methods. Then we went for function structure, where for any device or any design for that matter, you classify into three categories, that is energy flow, material flow, and information flow. Then we will discuss concept generation in the upcoming classes. So now I think you can understand what is a product function, what is functional decomposition, and how do we use a common basis function vocabulary, why it is important. And the method that we are going to follow is verb plus noun. Instead of saying motor, we will say generate torque. So we are not going to go with component specific discussion. We'll discuss in terms of the function, that is verb plus noun. Then what is the difference between function tree and function structure was discussed. Then we saw three major flows, that is information, then we saw material, then we saw energy. These three types of flows we discussed with different examples. Then we also saw what is a black box model, and we discussed um, what is a subtract and operate method. That is SOP means you will consider one component, fundamental component or low level component, then we'll remove that component, subtract it, and see what are the functions that are getting lost. If we do that, we can understand the function of each and every component. Then we also discussed why and how questions used so far. So I think now you will be able to take up the assignment, subjective assignment also. So with this, I would like to conclude today's live session. If you have any questions, you can ask now. So today we have discussed week 6 lectures. Next week, next Monday, We'll discuss week 7 lectures and the assignment that needs to be submitted. So if you have any doubts in assignment 6, you can ask now. That is week 6 assignment, you can ask now. Next week, we'll discuss week 7 lectures and the assignment that has to be submitted on 9th of September. So after the lecture, I'll be sharing the material. You can get the PPT material if it is useful for the assignment. You can make use of it, and I also think that it will be useful for your exam preparation during the month of October. Mr. Shakib, do you have any doubts? Mr. Mohammed Shahib? If you have any questions, you can ask me. So, thank you everyone for patient listening. So, we'll close the session. Since there are no doubts, we can close the session and I'll leave the meeting. Thank you.